a volume of X meter cubed transfers to the tank. Because of that, the level of the water rises from H0 to a value Hp. Hello, welcome to Understanding Power Electronics. In this video, we will see an idea called charge balance in capacitors, what it is, and how it is useful in power electronics. With that as our view, let's get started. There is a previous video in this series called voltsecond balance. That's for inductors. This is charge balance for capacitors. There is an idea called duality in circuits. This duality idea is there in other areas also, for example, in mechanical engineering. In electrical circuits, duality can be briefly explained as follows. Voltage and current are dual of each other. So voltage is a dual of current and current is a dual of voltage. Resistance and conductance are dual of each other. Conductance is of course 1 over resistance. Suppose we take the Ohm's law, V is equal to Ri. If we substitute V with I, R with G, and I with V, then we will get the equation I equal to GV. You can note that the form of this equation is exactly the same of this equation. That is what duality is about. The equations are similar. There is a symmetry about these relationships and variables. So V equal to Ri and I equal to GV are duals of each other. Likewise, inductance is a dual of capacitance, and capacitance is the dual of inductance. So I can write V equals L di by dt. I can substitute I in place of V, C in place of L, and V in place of I here. So in which case we can write I equals C dV by dt, which is of course the equation for capacitance. So it shows that inductance and capacitance are dual of each other. Kirchhoff's voltage law and Kirchhoff's current law are duals of each other. If you have a series resonant circuit fed by a voltage source, you can have a dual circuit, a parallel resonant circuit fed by a current source, and so on. There is an idea that is often used in power electronics, which is called voltsecond balance in an inductor. There is a video about it in this series. We can have a dual of this. Replace volt with ampere. Replace inductor with capacitor. Then you will get ampere second balance in a capacitor. And what is ampere second? That is charge, coulombs. So just as an inductor under steady state exhibits voltsecond balance, a capacitor under steady state will exhibit charge balance. In this video, we will see what charge balance is in a capacitor under steady state and how it is useful in power electronics. Consider a capacitor in steady state. Steady state means the DC voltages and currents in the circuit have all reached constant values. They are not changing anymore. And the AC voltages and currents, or the ripple voltages and currents, are the same cycle after cycle. This is a symbol of a capacitor. Vc is the voltage of the capacitor. IC is the current in the capacitor. IC equal to C dVc by dt is the current voltage relationship in a capacitor. Now we will take some voltage waveform under steady state. Y-axis is going to be the capacitor voltage, x-axis is the time in milliseconds. So this is a periodic waveform. We have arbitrarily taken it. Let us take that this is the voltage that is obtained in a power electronic circuit. The DC voltage can be non-zero It can be positive, it can be negative, or it can be 0. Here it is negative, some value. The capacitor voltage starts from V0 at t equal to 0, reaches a value of Vp at t equal to t1, and then returns to Vt at the end of the cycle. The period of the cycle is capital T. You can see that this is a periodic waveform because we are under steady state. So under steady state, Vt equal to V0. That is the main thing. Now let's see how the current waveform will look like. At t equal to 0, dVc by dt is 0. So because of that, the IC will be 0. Between t equal to 0 and t equal to t1, the voltage is always rising. The slope is always positive. That means that the capacitor current will always be positive. At t equal to t1, the capacitor voltage is Vp and dVc by dt is 0. So IC will again be 0 at t equal to t1. So the current will start at 0, will reach a peak where the slope dVc by dt is maximum, and then return to 0 at t equal to t1. Between t1 and t equal to capital T, the voltage is continuously falling. The slope is negative. dVc by dt is negative. So that means IC will be negative. At t equal to capital T, once again IC will become 0 because dVc by dt is again 0. So let's see how we have done in guessing the current waveform. And you can see that the current waveform is as we expect. It starts from 0 here, reaches a peak here, and then comes back to 0 here at t equal to t1, and then goes negative, reaches a negative peak here, and then returns here at t equal to capital T. Now we will take this equation IC equal to C dVc by dt and write it in differential form. So 1 over C IC dt equals dVc. We will integrate this both sides between t equal to 0 and t equal to capital T. On the left hand side, the integrating variable is t, so the limits are between 0 and capital T. On the right hand side, the integrating variable is Vc. So the limits will be the values of Vc at t equal to 0 and at t equal to capital T. So this will be 1 over C integral 0 to capital T IC dt equals V0 to Vt dVc. Integral dVc is of course Vc, and applying the limits, we will have Vt minus V0, and this is the main thing, Vt equals V0, because we are under steady state. And since Vt equal to V0, this equals 0. So 1 over C integral 0 to t IC dt equal to 0. What that means is integral 0 to capital T IC dt equals 0. This is charge balance because integral IC dt is charge. So this is the net charge going into the capacitor or out of the capacitor over a cycle under steady state, that is 0. That's what this equation says. Next, we will just quickly see the relationship between charge balance and DC current in a capacitor. The average current under steady state and DC current are the same. Average current is given by 1 over capital T integral 0 to t IC dt. If you have some discrete items, you add up all the discrete items and divide by the number of discrete items. In a continuous function, you integrate the function over a whole period and then divide the integral by the period. Now this integral 0 to t ic dt, that is our charge balance expression, and that is 0. So average DC current is 0 in a capacitor under steady state. Whether we talk of charge balance or the fact that capacitor cannot handle a DC current under steady state, both mean the same. Next, we will understand this charge balance a little bit deeper. This gives the charge balance equation. Integral 0 to capital T IC dt equals 0. You are integrating over a whole period from t equal to 0 to t equal to capital T. Let us split the time interval into two intervals, between 0 and t1 and between t1 and t. So in which case you can write the integral as integral 0 to t1 ic dt plus t1 to capital T ic dt equal to 0. Between 0 and t1, ic is always positive. So this is the charge going into the capacitor. Let's call that Q plus. Between T1 and capital T, IC is always negative. So this is the charge that is going out of the capacitor. Current is going out. So this is Q minus. So Q plus Q minus equals 0. Or Q plus and Q minus are equal in magnitude. The total charge going in a cycle equals the total charge coming out in a cycle. Next, we will see a couple of uses of this charge balance idea. One obvious use is in detecting errors in our analysis. When we are designing a converter, when we are doing some problem, when we are analyzing, if you notice that the capacitor current is drawn in such a way that the charge that is going in is not equal to the charge that is going out, you know there is something wrong. So obviously it can act as a check. Another way it can be used, not often used though, is current ratio in some converters. I'm going to draw on duality principle here. That means I'm going to have a comparison with voltsecond balance in inductors. If you have not done that already, the voltsecond balance in inductors, it is okay. You should still be able to follow most of what we are discussing. So let's take a buck DC-DC converter. I'm not going to go into detailed explanation of this. This is only for simple illustration purposes. It's a step-down converter. The output voltage is always less than the input voltage. It's a DC to DC converter. The input voltage is DC. The output voltage is DC. Under steady state, we wish to find V0 by V in ratio. One method is we take the inductor here and apply the voltseconds balance to this inductor. So we take the inductor voltage waveform, equate the positive voltseconds with the magnitude of the negative voltseconds, and from there we can obtain V0 by V in ratio. When you do that under steady state, we get the well-known equation V0 by V in equals T. You can do a very similar thing using charge balance in certain converters. Let me show a converter. This is called as a Chook DC-DC converter. Chook is the inventor of this circuit. In this DC-DC converter, the output voltage V0 can be more than input voltage in magnitude or less than input voltage in magnitude. And notice that with respect to this common point, V in is positive, whereas V0 is negative. So the output voltage will be minus something. So if you give 100 volts input, you can get minus 150 volts as the output. You can get minus 75 volts as the output, but the output voltage will be of opposite polarity to the input voltage. So this is useful in those cases where we need to develop a negative voltage from a positive voltage. In is the input current, I in average is the DC input current. We are not going to the operation of the converter in detail, just to illustrate how charge balance can be applied. So I in average is the DC current from the DC source V in. IO is the DC current absorbed by the load. If I take a look at this node, the capacitor cannot absorb the DC current. We have already seen that. So this DC current should be flowing in this inductor. So I2 average is the load DC current, I0, and I in average is the source DC current. Now we notice that in this converter, there is a capacitor CT here in the middle. That is an energy transfer capacitor to transfer the energy from the input side to the load side. If we take the current waveform of that capacitor and apply charge balance, then we will get an equation for the ratio of the currents I2 average, that is I0, and I in average. We get the output current, output DC current, divided by the input DC current is D by 1 minus T, that is the current ratio. So you can use this charge balance idea to determine current ratios in inductors typically in certain converters. A common use of charge balance is in determining the ripple voltage or the swing in voltage of a capacitor. This shows a typical capacitor voltage in a power converter. We assume that the circuit has reached DC steady state. That means the average voltage or the DC voltage is constant and remains constant. And the capacitor voltage waveform and the waveforms everywhere are periodic. T is the period of the waveform. This is the average voltage or the DC voltage of the capacitor. The voltage starts from a value V0 and then goes to a peak Vp and then returns at the end of the cycle to a value Vt, which is equal to V0. So it is in steady state and it's a periodic waveform. One of the parameters of interest to the designer is the so-called peak-to-peak ripple voltage. That is the delta Vc, the difference between Vp and V0. We will look at an analogy and we will understand this peak-to-peak ripple voltage a bit more. Consider a tank of water. There is already some water, and then we have two taps, one tap A and another tap B. Tap A is opened and left on for some time within an hour. In 1 hour, for a small period, it is left on, and a volume of X meter cubed transfers to the tank. Because of that, the level of the water rises from H0 to a value HP. Now tap A is turned off and tap B is turned on. A tap B is turned on to let the same amount of water out. So in 1 hour, tap A is opened, X meter cubed comes in, tap B is then opened, and X meter cubed goes out. So when tap A is opened, the level of the water rises from H0 to HP. So when tab B is opened, we can expect the level to go back to H0. So again, in the next hour, it is repeated. Again, within 1 hour, X meter cubed goes in, and then X meter cubed is taken out. So the level will go from H0 to HP and back to H0, H0 to HP and back to H0. So the average level will be somewhere between H0 and HP. We can mark it here as H average. You can see the similarities. H average is similar to VC average. H naught is similar to V naught. HP is similar to VP. And 1 hour of duration is similar to the period T. Now, HP minus H naught is the swing in the water level. Notice that H average is determined by the past history of the water flow. Likewise, VC average is determined by past history of capacitor current. So, by using charge balance, we are not determining VC average. That is determined by the past history of charging and discharging. We are determining VP minus V naught by using charge balance. Likewise, here HP minus H naught is the swing in water level, and that you can determine by considering the X, the inflow of water every hour, divided by the cross-section area of the tank. That will tell you by how much the water level goes up. We can expect a similar solution in the case of capacitor under steady state also. That means delta VC, we can expect a similar formula. We will see that next. Next, we will consider a boost converter as an example. Some of you may not know what a boost converter is. You may not have studied it, but it is okay. We are just going to see that part of the boost converter analysis where this idea of charge balance is used to find the ripple voltage of the capacitor. So you should be able to follow the discussion here. Boost converter, as the name implies, boosts the voltage. It's a DC to DC converter. The output voltage is always higher than the input voltage. If the input voltage is 100 volts, we can get 125 volts output, we can get 150 volts output, but we can never get 75 volts output, for example. Capacitor C is a filter capacitor. It is parallel to the load and it ensures that the voltage, output voltage V0 is a reasonably good DC. So we are planning to find the ripple voltage here. There is of course a DC voltage across this capacitor. The output voltage is mainly DC, but our focus is on the ripple around that DC. In order to find the ripple voltage, we need to find the capacitor current. So let us start with the diode current, ID. The diode current ID comes because of the operation of the converter, and it has the waveform that I am going to show. Y-axis is the current and x-axis is time, here in microseconds. I have taken a specific converter and analyzed it. So we are going to deal with actual values of currents and voltages. The ID waveform looks like this. During this interval, the switch is off for 60 microseconds and the diode conducts, so the diode carries the current. And during this interval, the switch is on, so the switch carries the current and the diode is off. So T on interval, the diode is off. T off interval, the diode is on. This T on and T off refer to the on and off intervals of the switch. T on plus T off is one switching period. Here the one switching period is 100 microseconds. So the switching frequency is 1 over 100 microsecond, that is 10 kilohertz. This is 50 amperes, this is 40 amperes, and here it is 0 amperes. We can find the average of this diode current. It is simply the area of this trapezoid divided by one period, 100 microsecond. Trapezoid area is easy to find, so I leave that as an exercise here. So when you do that, the average current will be 27 amperes. That is the DC current. Please note that the DC current cannot flow into the capacitor. So the DC current should flow into the load. Let us assume that the load current consists of only the DC current. So the average current of the diode flows into the load, 27 amperes. The remaining flows into the capacitor. In order to see that clearly, let us write the KCL around node A. There are three currents, ID, I0, which is a constant value, 27 amperes, and IC. The algebraic sum of these three currents should be 0. So ID equals IC plus I0. We are interested in finding IC. So IC is ID minus I0 or ID minus 27 amperes. So we can obtain the capacitor current waveform from the diode current waveform by subtracting 27 amperes everywhere. So all we need to do is take the ID waveform and push the whole waveform down by 27 amperes. If we do that, we get this red curve. 50 amperes will become 23 amperes, 50 minus 27 is 23, 40 will become 13 amperes, and 0 amperes will become minus 27 amperes. In this part of the waveform, between 0 and 60 microsecond, the current is always positive. So charge is going into the capacitor. Between 60 and 100 microsecond, current is always negative. Charge is always going out of the capacitance. So Q minus is negative. Q plus plus Q minus must be 0. That is charge balance. Now let us see how the capacitor voltage waveform is going to look like. IC is C dVc by dt. So Vc will be 1 over C integral of IC dt. So if the current waveform is integrated, you should get the shape of the voltage waveform. Here current is always positive, so the voltage must be rising. Here the current is always negative, so the voltage must be falling. The average voltage is the DC voltage, which is obtained because of boost operation. This is the voltage waveform. You can see that between 0 and T1 interval, the voltage is rising. Between T1 and 100 microsecond, that is the end of the period, the voltage is continuously falling. The average voltage is Vc average, that is the DC output voltage, that is 409 volts. We are not dealing with that now. The voltage here is V0. When Q plus flows into it, it rises to Vp, and when the same magnitude of charge is taken out, it falls again back to V0. Very similar to the way the water level rises and then falls back when the same amount of water flows in and is taken out. Now what we are interested in is this delta Vc, the ripple voltage or the voltage swing, Vp minus V0. Delta Vc is of course called peak to peak ripple capacitor voltage. For that, let us express this in differential form. 1 over CIC dt is dVc. We will now integrate this between 0 and T1. T1 because at T1 the voltage is Vp. So integrating this between 0 and T1, we get 1 over C integral 0 to T1 IC dt. At t equal to 0, the voltage will be V0. At t equal to T1, the voltage will be Vp. On the right hand side, you will have integral V0 to Vp dVc, which is Vp minus V0 equal to delta Vc. This expression 0 to T1 IC dt is Q plus. So delta Vc will be Q plus by C, or Q minus by C, the magnitude of that. The total amount of charge going in or going out in one cycle is Q plus. Divide that by C, you get the delta Vc. In the case of the water tank example, the total amount of water going in is X. Divide that by the cross-section area A, you get delta H, the change in the level. So water and charge are similar here. The water level and the voltage are similar, and the cross-section area and capacitance are similar. This analogy is pretty good. It matches pretty well. But a word of caution with all analogies in general, please don't stretch the analogies too far, then they will break. In order to determine the value of delta Vc, you need to calculate either Q plus or Q minus. Q minus is a bit easier here because it's a rectangle. So let's do that. Minus 27 amperes times this interval, that is the on interval, 40 microsecond. So minus 27 times 40 microsecond, the magnitude, absolute value of that, 1.08 millicoulombs. In this example, the C value that I had taken was 200 microfarad. Then using 200 microfarad, we will get 5.4 volts. So the DC voltage is 409 volts, and around that you have a 5.4 volts ripple because of the switching action. This is a very important parameter. For example, in this case, it defines how good a DC it is. Suppose the specification called for 1% ripple. That means the ripple voltage has to be below 1%. 1% of 409 volts is 4.1 volt. So the peak-to-peak ripple voltage must be below 4.1 volt. Here it is above 4.1 volt, slightly, but it is above 4.1 volt. So what can you do? One obvious way is to increase the 200 microfarad. You put a larger capacitor. You can put a 300 microfarad capacitor. You can check out what the ripple will be. It will be less than 4.1 volt. So that's possible. Another way is to increase the switching frequency. I'll let you think about it. Why increasing the switching frequency will result in lower ripple. Yet another way is not to use the boost converter, but to go for another converter in which the filtering action is better. So you can see how important this can be in analysis and design. Another note, here we have assumed an ideal capacitor. In many cases, parasitic elements in the capacitor, such as series parasitic resistor, series parasitic inductor, can affect this ripple, and a designer has to be aware of it and check that also. In this video, we saw what charge balance is and how it can be used in converters. We also saw a bit about what duality is in electrical circuits and how charge balance and voltsecond balance are related. With this, we have come to the end of this video. In case you find this video and the series of these videos interesting and useful to you, please consider subscribing to the channel and also clicking the like button. Thank you.